Okay, everyone, let's get started. So we're going to finish up our unit on transformers and LLMs today. And this last section is just kind of a fun section on a nice application called Scikit LLM that lets you connect with these state-of-the-art models and use them for scikit-learn style tasks. And this is essential because you can't run these models locally. They're too big. And some of the applications that are supported by Scikit LLM are text classification, and there's various flavors of that we'll talk about. Text-to-text modeling, things like summarization, translation, text vectorization, and text tagging. So that would be like you give it a big piece of text and then you ask it to flag all the people's names in it or all the dates and things like that. So I'll show you some examples of a few of these. And in order to use these, you have to have an API key for the model that you want to use. So I'm going to be looking at OpenAI's models just because that's kind of the default, and there's many of them. They do have other models. If you want to use other models, you can check that out. You can use other models as well. And the OpenAI key is something that you have to pay for. I think you have to pay for $5 worth, but it goes a long way. Like in developing the demo, which I ran, many dozens of times, it was less than $1. So. You get a lot of use out of just a few pennies of your API credits. Okay, so we're first going to talk about a type of classification that we have not talked about yet, which is called zero-shot classification. And in zero-shot classification, there are no labeled training examples. So it sounds kind of strange. You only tell the target the class names, that's it. And you rely on the fact that this model has been trained with a massive amount of general pre-training so that it knows enough. Once you give it the categories that you want it to use, it knows enough about what those mean and how they relate to everything else that it knows. So we're going to demonstrate with a sort of a toy test data set that is part of skLLM. It's a 30 sample data set that has a few sentences of movie reviews, and then each one has a label that's either positive, negative, or neutral. And I'll show you some examples of this. To fit the classifier, it's not fitting in the traditional sense. All you have to do is tell it your label categories. That's it. So here's the code. So you can see we import skLLM models, GPT classification zero shot. That's the library zero shot GPT classifier. So we instantiate the classifier by basically just telling it the model we want to use. And then the fit line, you can see all that you're giving it is that you want it to use positive, negative, neutral. You're not giving it any features or any labeled data. You can also call it, if you have X and Y feature target matrices, you can call it this way, but I think it's a little bit misleading because it makes it seem like it's somehow using the numbers, but it's actually not. It's just extracting the label names from that. And then you just do CLF predict. So it's just like you would do with sklearn. And for the demonstration, for the demo code, I use the GPT 5.1 model, which is a pretty recent model and pretty fast and pretty cheap for the power. And this gave 90% accuracy on this 30 sample data set. Now it's different every time you run it, but usually it was 90%, sometimes a little more, sometimes a little less. So I was kind of interested to see what was actually happening when you do this. So there's a way where you can intercept the message that it is sending to OpenAI to see what it's actually doing. And it's very interesting and revealing. And so this is the message it's sent, and I don't exactly know all the different, the format of the API call, but let's look at the beginning. So there's, let me see, there's, I think there's really just, okay. So there's one thing here, it's role system content, and then that's in curly braces. And then there's another one, role user content, and I think the end of that curly brace is here. And then finally, there's model GPT 5.1 response format, and then some kind of formatting instructions. So let's look at the two. Maybe I'll color this other one a different color. Okay, so we have, I'll make it green. Okay, so the first one seems to be like a system level instruction, and then this green one is like a user level instruction. And in the system level instruction, it's very simple. It says you are a text classifier. And note that this is given in plain English. And then the next one is sort of the more detailed set of instructions. It is somehow labeled as the user, and it says you will be provided with the following information: an arbitrary text sample. The sample is delimited with triple backticks. A list of categories the text sample can be assigned to. The list is delimited with square brackets. The categories in the list are enclosed in the single quotes and comma separated. And then perform the following tasks. 1, identify to which category the provided text belongs to with the highest probability. 2, assign the provided text to that category. 3, provide your response in a JSON format containing a single key label and a value corresponding to the assigned category. Do not provide any additional information except the JSON. And then list of categories, positive, negative, neutral, and text sample. I think it's just giving this as an example. And this is one of the feature. This is, just an example I came up with. I was absolutely blown away by the performances in Summer's End. The acting was top-notch. The plot had me gripped from start to finish. Truly captivating cinematic experience that I would highly recommend. And then your JSON response. Okay. So the thing to note is that it's communicating with the model in plain English, plus a few kind of special words that are interpreted in a certain way, and that the instructions it's giving are very detailed, very clear, and sort of very, very well spread out. And that's it. So it's an example of like a good prompt for these models. So I don't really have, for this example, you can look at the demo. I just had it run this 30 sample test set and then compared to the ground truth labels, and it was 90% correct. Any questions on this? Okay, so basically, what this package is doing for you is that it is constructing these prompts, and then it's handling the data that comes back, and from that data kind of unpacking it and making it easy for you to use in a scikit-learn style format. Okay, so if no questions, we'll move on to second, a different kind of classification problem. And this is multi-label. Okay, so just to review what we're familiar with multi-class classification. And as we know, in that case, the model produces a PMF across classes. And when it wants to make a hard decision, it reports the single class with the highest probability. So that's what we learned about so far. But this is new, multi-label classification. So in this case, you give it a list of labels, and it generates a probability value for every class. And to make a hard decision, it reports all the classes whose probabilities are greater than 0.5. Okay, so basically it's doing a bunch of parallel binary classifiers. So, for example, we'll do an example where the class labels are romance, action, sci-fi, other. So in the traditional multi-class, this would be, you could only choose one of these, right? That's how multi-class classification works. You have to choose the best of these 4 options. But in multi-label, basically, you can have any of these appear or in any combination or none of the above. Okay, so the question is sort of in parallel, is it romance or not? Is it action or not? Is it sci-fi or not? Is it other or not? So that's the problem. That's basically multi-label classification. To train these sorts of classifiers, what you do is you just put binary cross-entropy on every one of the outputs of your model, rather than cross-entropy across the outputs. So just a small change, but it turns it into a very different kind of a classification problem. Okay, so basically in this case, we're going to do this multi-label, but we're also going to do multi-shot. So this is, zero shot. So it's going to be zero-shot multi-label. So that means that the classifier will just be given these 4 labels, and it's told, treat each one as a binary yes or no, and then just give me the list of yes options for every test feature. And so here we import the multi-label zero-shot GPT classifier. To fit it, we just give it those 4 categories, and then we're going to predict on the first 10 examples, just so I could fit them on a page. We don't have any ground truth labels because this data set actually, the way that it was labeled as it came is like this. So we're just going to try something new. We don't have any ground truth, but we can at least look at the answers to see if things look reasonable. Okay, so what I have here is I have this part is the feature vector that it was given, and then this part is a list of the labels that were reported as greater than 50% out of those 4 options. So, so basically, for this first one, this is actually the same example we saw that skLLM used as the example for the original zero shot. I was absolutely blown away by the performances in Summer's End. The acting was top-notch. The plot had me gripped from start to finish. Truly captivating cinematic experience that I would highly recommend. So this model is seeing, okay, is this romance or not? Is it action or not? Is it sci-fi or not? Is it something other or not? And this classified this as other and not as sci-fi, romance, or action. And I think that makes sense from what the feature is. Let's look at the next one. The special effects in Star Battle's Nebula Conflict were out of this world. I felt like I was actually in space. The storyline was incredibly engaging and left me wanting more. Excellent film. So basically, because of the star and space and special effects, I think it's reasonable to label this as probably a sci-fi movie, which is what it did. Okay, and then we have another example here which contains the word love, romantic storyline, romance lovers. No surprise that it tagged this as romance. And then we have only one example where it chose multiple categories. So this one, it chose as both action and other. Nightshade is a brilliant take on the superhero genre. The protagonist was relatable and the villain was genuinely scary. The action sequences were thrilling, the storyline was engaging. I can't wait for the sequel. So just as an example of what zero-shot multi-label text classification is. All right, any questions on this? Okay. All right, so next application, we'll talk about text vectorization. And basically, this is a very general, you could say problem or a very general application. And it's just the process of converting an arbitrary length text string, like this could be an entire book, or it could be a word, it could be anything, or part of word, down to a numerical vector. So that's what we're talking about. And once you have vectorized your text into numbers, now you can do anything you want with it from traditional machine learning. You could train a numerical classifier if you had features and labels that were numerical, or you could cluster the data. We haven't talked about clustering yet in this course, but we will, not in the coming chapter, but the one after that. So we'll learn about what that is. And there's many, many ways to do text vectorization. Traditionally, people, especially when you have very large corpuses of text like books or something, and you want to squeeze these down to a vector, they would use what are called bag of words models, like TF-IDF, and we will get into the details of that when we talk about clustering. They're kind of crude compared to what we saw for embedding, but basically these LLMs, they handle text vectorization via text embedding. Okay, so basically similar to what we had talked about before, you have your input text. You assume that this text, say, can fit in the context. And so you tokenize all those original words in your text or subwords, and then you pass it through all your transformer layers, and that helps to interpret those words in contexts, and it updates their embeddings, and now you have this long string of embeddings, long sequence of embeddings. And what we haven't seen yet is the last stage. They are pooled down to a single vector. And the word pooling is just a generic vector for squeezing down in dimension. There's different ways to do the pooling. So some of the older models, like this ADA 002, just averages the sequence of final embeddings. It just averages them down to the length of a single embedding. It's as simple as that. And so the newer models have slightly more sophisticated pooling strategies that you can read about if you like. But basically, at the end of the day, they have to squeeze whatever you give them down to a vector of, maybe like a few thousand or a few hundred length vector. So that's what we're doing. So I'll just give you one example. We're going to be using, so OpenAI has 3 different models that do text embedding, text vectorization. You cannot use any of their usual models, like GPT 5.1. You cannot do vectorization with that. So it is doing all the stuff you need for vectorization, but it's not set up to do the pooling stage and to extract the numerical values. So GPT 5.1 is set up essentially to do next token prediction. So even though it's kind of computationally doing what we need, there's no way to get out the information we need from that model, or at least OpenAI doesn't give you that option. But it does make 3 specific models, basically this ADA 002, and it gives you 2 versions of text embedding 3. This is the large one, there's also a smaller one. And so you can play with any of those, and there may be other text vectorizers from other companies beyond OpenAI that you can use, I'm not sure. So anyway, for this text embedding 3 large, it always gives you a vector of real numbers of length 3072. So that's basically what it gives you. No matter how long the input is, you give it a book, or if you can fit a book in the context, you give it a book, it will reduce it to a 3072 vector. You give it a word, it gives you a 3072 vector. Okay. And so now, just as a sort of a demonstration, we have these vectors. We can make these vectors, so I thought it'd be fun to visualize them in 2D. And this is actually the subject of the next chapter, is one way to visualize them. So essentially, we have these very high-dimensional vectors, but we, as humans, cannot visualize things in that high-dimensional space. So we're going to use kind of a simple idea of projecting those vectors onto a lower space, a 2D space. So when we project them down, now these are points in a plane, and we can visualize them as humans. Okay, and we will get into all the details of this whole projection process starting in a few minutes, but this is just the result of that. So what I did, I gave it, for this example, I gave it 6 words to see what would happen. So the words I gave it were a typical man, or the phrases I gave it, a typical man, a nobleman, King Charles III, an ordinary woman, a woman from the royal family, and Queen Elizabeth II. So it gave, 6 3,000 dimensional embeddings. I then projected them down using PCA, which we'll talk about in the next unit, PCA, principal component analysis. And now it gave me these 6 projections, and it's exactly how you would expect. So on one hand, you have a progression basically in this direction of royalty, from a typical man to a nobleman to king. Same over here, typical woman or ordinary woman, woman from a royal family, queen. And then you have another direction here that is gender. Male up, female down. So that's just what we would expect, and that's what happens with these embeddings. It's kind of cool. And then a similar one, I gave it a list of 8 text phrases: a long stale baguette, a big juicy bratwurst, a massive bowl of spaghetti, a very red borscht, and I gave it 4 countries: France, Germany, Italy, Russia. And so now we see that there is sort of a food to geography axis horizontally, and then we have another axis which is kind of, it puts France at one extreme and Russia at the other extreme, and Germany and Italy are halfway between. And you can see that it correctly gets the same ordering between the different, like the French baguette, the German bratwurst, the Italian spaghetti, and the Russian soup. So again, we see the sort of things that we would expect. Okay, it's fun to play with these, try different things and see what you get. All right, so any questions on text vectorization? Yeah.
Have you ever used this in your work?
So in my research, we haven't really done much with language. It was more, I do more images. So but for medical imaging, you definitely could use this because you might have some medical images like CT scans or MRIs that are images, but then you might have some radiologist reports, and you might try to say I want to classify this from both of those things. So now you could turn the text into numerics and combine that with the image and build a classifier, for example. Just one example.
Wanted to
Yeah.
have a practical.
Oh, I mean, yeah. Oh, you mean for text vectorization?
Yeah.
Anytime, because if you think about it, if you want to deal with text in any kind of research problem, you gotta, either you just get text from text, you could do that with language model, or you need to convert it to numbers to use it, right? So this is just a very simple way to convert it to numbers that you can do in a matter of, minutes, and, incorporate this in your project however you want.
It's so exciting. I'll play.
Yeah. Maybe it's useful for somebody. Okay, any questions? Great. So that's all I have for this chapter. If you guys have any requests for any other things that you think would be interesting to learn about, or maybe next time I teach the course I could use them, but this is all I have for this semester. But yeah, I'm curious what you guys think. If this was useful, or because there's obviously a lot of material here. It's quickly changing. So, all right. Any other questions on this unit? Large language models, transformers? Okay. Also, like in terms of using this stuff for your research, transformers, even though we discuss them for text and a little bit for images, they can be used for general data. So like if your data is like some sort of time series, or even spatially, you could say it's like a two-dimensional. You'd have to make a series out of a 2D thing, but once you have that, then you can just treat those numbers as inputs to an embedding stage, and you can use transformers as you wish. You can use transformers in the final project if you want to try them. Like, I have no idea whether they'll be useful or not, but it's, once you've done the MLPs, you're looking for something else. Transformers are certainly something you could try.
We can use transformers for the final project, or does that not fall into?
It's a neural network.
Oh, that counts?
It's just a neural network that has a, it's a little bit more specific than a MLP, right? It has this attention layers and MLPs.
Gotcha.
So all that you need is you need your input to be a sequence of vectors. So anything that you can get as a sequence of vectors has the right format to then be worked on by a transformer.
Gotcha.
Yeah.
So what are transformers like bad at?
Well, yeah, great question. So the challenge of a lot of transformers is there's a lot of parameters to learn relative to a simple MLP. And they're trying to learn a lot of stuff. And so what you find is that maybe if you don't have too much data and you train a transformer, it's not working very well because it's just like maybe an overly complicated model for the amount of data you have. So so there are, the more structured your model is, essentially the more, it's this bias variance trade-off. Like if you make a model structured and good at doing a very specific thing, then it can do that thing very well, maybe very efficiently, but then other things maybe not as good at. So we haven't talked about them yet, but, or I don't know if we will this semester, but prior to transformers, people used other things like RNNs or convolutional neural networks. These are all networks that have a very particular structure in them. And in some sense, they might work really well for smaller data sets because there's not as many parameters to learn. But then once the data keeps getting bigger, they kind of hit the ceiling. But transformers can be scaled. And if you have enough complexity and if you have enough data, they just keep working better and better and better. So yeah, for the final project, like maybe there's not enough data to train a transformer to the point where it works better than a simple MLP. I haven't tried it, I don't know. But that could be the thing. And the complexity also it grows quadratically with the context because you end up sort of learning this matrix of attention weights. Whereas for a lot of models, the complexity grows linearly. So that's another kind of bottleneck with transformers. And there are some versions of attention that have been, where people want to make them run faster, and so they use low-rank approximations and different things to speed them up at the expense of losing some power. But in some cases, that's a much better trade-off. So there's ways to kind of make them more lightweight, speed them up, that could be played with. Okay, good question. Any other questions? Okay, great. So let's move on to unit about low-rank matrix factorization. And I didn't actually realize it until your question now, but these ideas are actually used in transformers when you're trying to speed them up. This is probably the the main way people do it. But we won't actually be talking about that. We'll just be talking more generally as, what is matrix factorization? What can it do for us? And we'll see two examples of it. Okay, so in the most general sense, matrix factorization goes like this. You have some data matrix. The data matrix can be, can really be any kind of data that you have collected. And in this case, I chose the dimensions in a familiar way, because whenever we have seen a data matrix X, we have seen it constructed by vertically concatenating the rows of our features, right? And so this would be N is the number of samples in our data set, and D is the number of features. So you're welcome to think about it that way. However, it is more general. We might have data that doesn't really fit that kind of, we don't think about it as like just rows of features. It's just some other two-dimensional data we've collected, and now we're trying to approximate that by a low-rank product, or a product of low-rank factors. So as you can see, if I multiply those two matrices, I do get the dimensions of this. But if you look at how many numbers you have to store here, you have to store n times d. Here you store n times r plus r times d. And just visually you can see that there's going to be less numbers to store here compared to here, especially if you choose r to be small. And r is a design choice. This is called the rank. So basically, as r gets bigger and bigger, once r gets to the size of d, this is not an approximation. It's just a different way of writing x. But if r is smaller than the rank of this matrix, then this is going to be an approximation. And the smaller that you make r, the worse the approximation gets. But the more you have kind of compressed your data or reduced how much data you need to store or work on later. Okay, so this is kind of the high-level idea behind matrix factorization. And at a high level, we can say that this is a form of unsupervised learning because we don't have any targets we're trying to predict. Applications would be dimensionality reduction. So if we think about these as samples of a data set, then these would be some new samples of that data set, which are reduced dimension from D down to R. And this would be sort of like a way to translate these samples from this dimension back up to this dimension. So this could be kind of like a dictionary or a key or something, and then these are your new samples. And then with that idea, maybe we can just do classification on these samples versus these, and then our classifier will run quicker because R is less than D, for example. So that could be examples of dimensionality reduction, or maybe we just want to store the data in a more compact way. Okay. Another application of this is modeling of latent structure. We'll talk about that a little bit later. So the idea is that you collected this data, but there is a pattern to the data that basically says that all the columns, or let's say all the rows, are really just different flavors or different linear combinations of a few kind of important vector directions. Or you could say simultaneously the same for the columns. All the columns in X are really just linear combinations of a few fundamental column types. And so this is really useful when you're, how many of you guys have heard of the Netflix problem? So the Netflix problem was a problem that Netflix proposed, I don't know, maybe about 15 years ago, where they had a bunch of data, and they had users on one dimension, and they had movies on the other dimension. And they had, so for every user, they would have the movie ratings for the movies that user had seen. And of course, they have a big library of movies, so a given user has only sampled, a small fraction of the movies. And then each movie, if you look this way, each movie has only been seen by some small fraction of the users. And so basically, this matrix had a lot of missing entries. About 99% was missing. And their goal was to fill in the missing entries, which corresponds to predicting the ratings for a movie you have not seen. And if you think about this from the low-rank matrix perspective, it kind of says, okay, even though we have like 1 million movies or whatever, maybe there's really only like a few kinds of movies. There's just our kinds of movies out there. There's like your comedy, your action, your horror. And then maybe we can model any movie as just sort of a linear combination of those fundamental movie types. Simultaneously, you could say there's really only just a few kind of users out there. There's users who like horror, users who like comedy and stuff. So these are the few kinds of user types, and all users can be modeled as a linear combination of those rows. And so this is just a way to do the modeling, and then now that you have the model, this latent structure in your data, you may actually, even though you have a sample, just a few samples, that may be enough to learn that many numbers, right? Because you count up like the unknowns you have, maybe that is smaller, or maybe that's smaller than the total number of samples you have here. So that's just an example. We'll talk a little bit more about that later. And then the last one is visualization. We just saw an example of visualization. In the last unit with text vectorization, we had 3,000 dimensional, so these were like 3,000 dimensional things. We wanted to squeeze them down. Actually, sorry, it's this way. These were 3,000 dimensional things. We wanted to squeeze them down to 2 dimensions. And we used PCA, and PCA is doing exactly a version of this. So just a few examples for why one would want to study matrix factorization. Okay. Any questions? Okay, so so linear dimensional array reduction, I talked about this already a little bit. So let's think again about X as a matrix whose rows are data samples. So we have always called these X sub I, and since these are rows, they have to be transposed. And the factorization that we're looking for, I think I'm using exactly the same notation. So if I look at the ith row here, then that would be the ith row here times that matrix. So xi transpose is zi transpose and times b transpose. Now, we can just transpose both sides of this equation to make it look a little prettier, and then you have this. Sorry, I meant to actually put an approximation sign here. Okay. And here. Okay, so here's another way to think about the approximation. And if you unpack this matrix vector product, we can write it like this, where you have a sum over the different columns, bj of b, and you have the scalar coefficients within this zi vector. So you could say that to construct any sample in your data set, you have this kind of these building blocks. So the columns of this are building blocks that you use to construct any column, or maybe any row of this. And these are the coefficients. So for sample I and building block j, you have a scalar coefficient zij. So that's how we're doing the approximation. So this is now going to be a linear approximation of our data. These are linearly combined to approximate this. And as we said before, if you choose the rank of the approximation R, which is the number of these coefficients, much smaller than the dimension in your original data D, you reduce your representation of that sample from D numbers down to R numbers. And this is basically a form of lossy compression. It's lossy in the sense that it's usually not going to be an exact equality, but it does reduce instead of working with D numbers, now you're working with R numbers. And if you bring R all the way down to 2 or 3, you can visualize it, and that's exactly what we did. We use R equals 2 to visualize it in those text embeddings. And again, this is a linear approximation, so you're making a linear approximation. So that's not the most sophisticated thing you can do. It definitely has its limits. So if you really want to do a better compression scheme, more sophisticated, you need to use something nonlinear. And that's potentially going to work way better. But the reason we're looking at linear is because it's relatively easy to study and compute, and these are very classical ideas. PCA is a super classical idea, so I think like if you're taking a course in machine learning, you should at least talk and learn about PCA a little bit. As it's something that everyone just sort of assumes you know once you're done with machine learning course. Okay, so this is one way to think of dimensionality reduction, why we're doing it. Any questions? Okay. All right, so let's look into the first way to do this. So PCA is the first way we'll do this. And rather than working on the raw feature vectors xi, what we're going to do is we're going to compute the sample mean from our entire data set, and we're going to subtract that, and we're going to work with these mean removed features, and we're going to call these things x tilde. That's the xi with the mean removed. And that's actually what we are going to approximate. And once you have this approximation, if you want to add the mean back in at the end, that's fine. You can definitely do that. But to do our approximation, we're going to work on approximating the mean removed vectors. And yeah, R, once again, is the rank of the approximation. And the notation, I guess the notation hasn't changed. This is exactly B times Z. Okay, so this is the setup that we've seen. And so the second main idea behind PCA is that we are going to jointly design the B matrix and all the ZI vectors to minimize RSS. So what that means is we have a sum over all our data samples, and then we have the squared Euclidean norm between x tilde I, the mean removed xi, and its approximation. So this is the same problem that we saw back when we were doing linear regression, except when you look at these quantities, things are different now. These are not targets. These are not, it's not like a matrix of features times prediction coefficients. It's same high-level ideas, but applied differently. We're just trying to, this is our data. We are trying to approximate it using some low-rank version. So this thing is called Principal Component Analysis, or PCA. How many of you guys have heard of PCA? Okay, great. So now you should be careful in doing this, because this choice of RSS is done mainly to make the problem tractable. There are some problems where this might be exactly what you like to do, but in other cases, doing this could actually lead to an approximation which is very poor performing, depending on what you want to do later with your data. For example, if you start with some raw features xi and you want to classify, you would also, of course, need labels if you want to do this, but if you want to classify these features, and you say, well, my classifier takes too long on the raw features, so I want to squeeze them down to a lower dimension, that will speed up my classification. And so you can figure out how to do that, and then you can just classify based on these reduced dimension ZIs. Well, the problem is that maybe when you have done this approximation, the information most useful for classification could have gotten stripped away. And so your classifier won't work as well. Okay, so yes, it will run faster, but it won't work as well. So we don't usually recommend this if your goal is to maximize performance. So on your final projects, there's always people that try PCA, and this definitely will speed things up. It will speed up the training and inference, but it will not improve your performance. So it's not generally something you want to spend time on, unless you're just curious. Okay, so that's kind of the setup of PCA. Are there any questions about the main ideas? Okay. So now I'll describe what the solution is, and later on, maybe we'll prove it. But I'll just kind of skip to the punchline here. So the RSS optimal basis, matrix B, we'll call that B hat, is going to be, you can compute it as a matrix, we'll call it capital VR. This as columns has the R principal eigenvectors of the sample covariance matrix. So if you remember back in Unit 2 when we talked about sample covariance, typically we would write it, you have like your xi, and then you would remove the mean, and then you have xi transpose with the mean removed. Well, we've already done the mean removal to make x tilde, so that's why we don't explicitly see the mean removal here. But this is exactly the covariance expression that we saw back in Unit 2. It's going to be matrix valued because you have a row times a column, so that gives you a square matrix. This is a D by D matrix. And so what you do is you take that matrix and you perform an eigendecomposition on that matrix, and you will get some eigenvectors that end up being orthonormal, and you get some eigenvalues that end up being non-negative, lambdas. And so this is, maybe how you compute this covariance matrix Q. Once you do the eigendecomposition, you could write it this way if you want. And in fact, I think maybe this was even on the very first midterm. You could write this if you want a V matrix times a diagonal lambda matrix times a V matrix transpose. So this is a square matrix with, along the diagonal, it has these lambda j's. Okay. And typically when you compute PCA, you find that the solver organizes these lambdas in the order from biggest to smallest. And so then likewise, the columns of V, you could say, also have that ordering. You have the most important column is first, the second most important, second, and so on. And I say most important because the strength of the lambda tells you how much of that vector will actually be part of Q. So if you have like a tiny lambda, it's not very important to construct Q. You can get rid of it without affecting Q much. But if you have a big lambda, that's important for constructing Q. So basically, when we say the principal eigenvectors, we mean the eigenvectors corresponding to the largest lambdas. Okay, so that is how you construct this B hat, is you construct Q. I mean, we'll learn a faster way, but you can construct Q, then you perform this eigendecomposition on it, then you look at your V matrix, which will typically be square, and you just choose the first R columns of it, and those are the most important orthonormal vectors for constructing Q. So that's part of what we need to do, is we need to get the B's, and then the second question is, how do you get the ZI's? Well, it turns out that those are also easy to compute. You take that same matrix, VR, and you transpose it and multiply it on the left by your mean removed data, and now it will squash it down to dimension R, and those are the coefficients. Those are the optimal coefficients. Okay, so let's look at some examples. So let's say we have a data set which has three-dimensional vectors. So we're plotting in 3D here. Actually, so the origin is, where is the origin? The origin is like somewhere here. Okay, so our original data are these points in R3. And don't be confused by the colors. The colors are not labels. They're not binary labels. The colors are just used to show which ones are on one side of this plane and which ones are on the other side. Okay, so let's say that's our data, or these set of three-dimensional vectors. It looks like we have, I don't know, maybe like 50 of them or so in this data set. And let's say we want to squeeze this down to two-dimensional vectors, which are closest to the original three-dimensional data in the right basis, or in the right subspace. So the goal of PCA then is to first of all find a plane if we want to squeeze it down to two. So we want to find a two-dimensional plane that lives within this three-dimensional space such that the errors, which are the distances between the 3D points and their closest point in the plane so that those errors are minimized in some square. So it's trying to minimize all those squared errors. Okay. This might look kind of familiar if you think back to linear regression. Let me ask, is Thomas Wu here? Okay. Yes, is Eric Wang here? Yeah, so Eric, do you remember back in Unit 2, we had a similar picture of regression where we were fitting two coefficients, but it was a little different than this. Do you remember what was different about that picture? We were also trying to minimize the size of some error vectors.
That's in 2 dimensions, but this one is 3 dimensions.
So we saw a three-dimensional picture, though. We had, we were trying to fit two coefficients, and so we had 3 dimensions. Do you remember at all how that differed from this picture? It's kind of a key difference. Does anybody remember? So in that case, what did we have on the vertical axis? Maybe we had like beta 0 and beta 1. Those were the things we could, is that right? Yeah, I think beta 0, beta 1. And then what did we have on the y-axis? Sorry, on this axis. Yeah, it was the targets. Right? So in that case, the difference is that all these errors, they were all vertical lines. So now they're perpendicular to the plane. So as you turn the plane, like if you put the plane like here, then the errors will always be perpendicular. Okay. So I just kind of want to point out the similarities, but there's differences too between what we saw before. Okay, so we have 3D data, which are these points in 3D, and we want to find the best 2D data set that approximates them, best being closest in the squared Euclidean sense. And so what PCA determines is it finds this particular plane, which is the plane that best matches, like the approximations in this plane have the best approximation error. Okay. Now, let's say that you said, no, I don't want to squeeze this down to 2, I want to squeeze it down to dimension 1. So now you have a one-dimensional subspace within your three-dimensional ambient space. So instead of a plane, now you have a line. And now the errors are all the distances from the original points to their closest projections on the line. And you want to orient the line in a way that minimizes those sum of squared distances. Okay. So this is a visualization of what we are doing when we run PCA. We're trying to find a subspace that best matches the data. And this is mean remove data, and subspaces always have to go through the origin. If you shift a subspace up from the origin, it's no longer actually a subspace. So we're finding the best subspace, it has to pass through the origin, and that's why we want to mean remove our data so that our data is also centered around the origin so we can kind of get a good match to that. Okay, so when we did the text vectorization example, we had these 3,000 length vectors, so we had a very big ambient space, and we wanted to, again, bring it down to dimension 2. And we had, I think, like 6 vectors in 3,000 space, and so we mean removed them, and then we wanted to find the best plane that fit those, and that's what I plotted for you. Okay, all right, so that's PCA. This is kind of what we're trying to do. This is the solution. Are there any questions on this? Yes.
Yeah, so like the vector representation then would be like if on the plane I drew a new coordinate system.
Exactly.
Then, okay.
That's exactly right. Yeah, let's talk about that more. So the origin, I don't know, I think the origin might be here. So yes, there's now going to be a new coordinate system. So like this is going to be Z1 and this is going to be Z2, right? And now when is that the right? We have to be a little careful. So if you restrict yourself to this plane, then these two-dimensional vectors are like your Z vectors. But if you think of this plane in 3 dimensions, then, and now you think of like, this is some 3-dimensional vector in this, larger space, this guy would be one of the B vectors. Because the B's are 3-dimensional things and the Z's are 2-dimensional things. If that makes sense. Okay. And then over here, let's say the origin is here. So Z is just a scalar. And so positive Z might go this way, negative Z might go that way. But then, like, where is this line oriented within the 3-dimensional space? Well, that is the single B vector, is exactly where that line is pointing in 3D. So those are the different visualizations. Okay, great. Any other questions? Okay, so this is the perfect time to stop because the next thing is to kind of get into why is that the solution, but we can save that until next time. If you didn't pick up your exams, I have them here, so feel free to pick them up.